Hello everyone, today we are going to see an example of a topological space that has the uniqueness of limit property, but that is not Hausdorff. By uniqueness of limit property, I mean the following. If we have a topological space X, then we say that X has the uniqueness of limit property if and only if, by definition, if an is a sequence in X such that it converges to L1 and L2, then L1 is equal to L2. Okay, this is the uniqueness of limit property, and we know that if a space is Hausdorff, then it has the uniqueness of limit property. The proposition is easy to be proved. I will not prove it. X Hausdorff implies uniqueness of limit property. Okay. Now we are going to see an example of a space that has the uniqueness of limit property, but that is not Hausdorff. And the idea behind the example is the following. The idea is the following. If we have a space X such that for any sequence an, if an converges, then an is definitely constant So let's see that if x is t0, that is points are closed, then x has the uniqueness of limit property. Okay, so let's prove this. Let an be equal to b for any n greater than or equal to n0. This implies, since an is definitely equal to this means that an converges to b. Let L be an element of X that is not B. We can prove that an cannot converge to L. Indeed, if you consider the open set X minus B, this is open because it is the complementary of the point B. This is an open set. This is since it is open and since it contains L, it is a neighborhood of L. So by definition of convergence, if by contradiction we had that an converges to L, this would imply that there is an n1 such that an is in X minus B for any n greater than n1, greater than or equal, but this is impossible since an is definitely equal to b. So we have proved that if an is a convergent sequence, since it is definitely constant, so it is definitely equal to b, then the only limit is b, because it converges to b because it's definitely constant, and if we take another point, it cannot converge to that other point. So we have the uniqueness of limit property. But we can try to construct a topological space of this kind that is not Hausdorff. And the example is the most natural way of constructing it, because it forces the sequence to be definitely constant if it converges. And the topology I'm talking about is the co-countable topology. Co-countable. We can put this topology in R, for example. So we call this topology T. And what is this topology? This topology is the topology such that the open sets are the complementary of countable sets, of countable subsets of R, or the empty set. Okay, it's easy to see that it is a topology because if you take C1 and because empty set and R are closed. We can check the property of the topology on closed sets, but it's the same. We have that the empty set and R are closed by definition. We have that if C1 and C2 are closed, then we have two possibilities. If one of them is R, if C1 equal to R or C2 is equal to R, then their union is equal to R, and so their union is closed. If they are both not equal to R, then their union is still countable because they are both countable. So their union is closed. If we take a family, an arbitrary family of closed, then we have two possibilities. The first one is that every set in this family is R, and then its intersection is still R, and so this means that the intersection is closed. If there exists a set in this family such that it is not R, then it means that Ci is countable, but then this means that the intersection has a cardinality that is less than the cardinality of Ci, and since Ci is countable, also the intersection is countable, and so the intersection is closed. So we have checked all the properties. So T is indeed a topology, and why does it have these properties? Because it is clearly T0 because the points are countable. So every element is the singleton of every element is a closed set. And we also have that if AN is a sequence, then such that AN converges to L, then AN is definitely equal to L. And we can prove it in a very easy way. Because if you assume by contradiction that there is a subsequence ANK such that ANK is not equal to L for every k in N, then we can consider the open set A that is equal to R minus ANK for every k. So this is an open set because it is the complementary of a countable set, and it contains L. So since this is a neighborhood of L, by definition of limit, we have that there exists an and 0, such that an is in A for every n greater than or equal to n0. But this is a contradiction, because since this is a subsequence, we have that we can find a k tilde such that nk tilde is greater than or equal to n0, but this would imply that an k tilde is in A, but this is impossible because an k tilde is not in A by the definition of A, because an k tilde is in this set. So we have proved that R endowed with this topology is T0 and it has the uniqueness of limit property. But we can easily see that R with this topology is not Hausdorff because, for example, we can take, I don't know, two numbers, x and y, that are different. And if we take a neighborhood of x, and we take b neighborhood of y, then we have that, for example, we can take these two to be open neighborhoods. So since they are open, we have that A is equal to R minus C with C countable. And also we have that B is equal to R minus D with D countable. So their intersection is equal to the intersection of these two sets, but this is equal to the complementary of the union of C and D. But since C and D are both countable, this implies that their union is countable. And so R minus a countable set cannot be the empty set. So we have proved that the intersection of A and B is not empty, and so it's not possible to find a neighborhood of X that is disjoint from a neighborhood of Y. So R with this topology is not Hausdorff. So this was everything for this video, and ciao to everyone.